All right, welcome for the next kind of central lesson in this whole unit that we've got, which is about balancing chemical equations. So we kind of in the last unit learned about, or last lesson sort of learned about how to decode some word problems, and here we're going to actually work on the physical process of learning to balance them. There's kind of an art to it, there's kind of a trick to it. Definitely requires some patience and an eraser. So we'll see how this goes, but you have some patience with yourself as you're practicing this particular skill, because it can be a little bit frustrating, but once you get the hang of it, it goes pretty quick usually. All right, so chemical equations, just as a reminder, vocab, we're talking about these sort of symbolic representations of a chemical reaction. The chemical reaction itself occurs in a beaker, but we're talking about how do we represent that on a piece of paper? What does that look like? When we do these, we always have some similar processes that we use. For example, reactants are always written on the left. There's products are written on the right, and there's an arrow sort of between the two of them that tells us that the reaction is going from reactants to products and not some sort of vice versa kind of thing. A lot of times there's some additional information in a balanced chemical equation that would include things about physical states, such as solid, liquid, gas, or aqueous. And potentially there may be information in there about energy changes, whether energy is going in as a reactant or coming out as a product. Just kind of depends on the story, so sometimes you don't need to include those. When we're talking about chemical equations and reactions in this, one of the important things to keep in mind is that this is all because of the law of conservation of matter. Matter cannot be created or destroyed in normal chemical reactions. We can do it in nuclear reactions if we're trying to do fission or fusion or something crazy like that, but in typical rules of basic chemistry like we're going to do in a Chem 1 class, or a Chem 2 class for that matter, you're still going to be making sure that the same elements that went in come out, and the same number of atoms of each thing that went in also have to come out. You're not allowed to just sort of make up new numbers of atoms, or have atoms magically appear and magically disappear. Whatever goes in has to come out. They have to match. So unfortunately, this can make writing our balanced equations sometimes a little bit more challenging. Writing unbalanced equations is hard enough because you have to remember all your names and formula rules and be able to interpret all these problems, but then having to go through that extra step of balancing it to make sure that it accurately reflects what's going on at the atomic level can be a bit of a challenge. It's one extra piece that you have to add on to it. So in terms of what these are, we're trying to make sure that when we write out our formulas that they match. So for example, if I wanted to write the equation for the formation of water from hydrogen gas and oxygen gas, it's kind of obvious that we've got hydrogen and oxygen present because they're on the left, hydrogen and oxygen gas, and on the right we've got H2O, which has hydrogen and oxygen. But trying to figure out the exact ratios, the numbers and types of atoms or molecules that come into contact with one another can be a little bit less obvious to see. And it's like, why can't I just write it like that? It looks perfectly good to me. Well, you can't quite, because the way it's written here, it kind of looks like one of the oxygens has just sort of magically disappeared. We've got one, there's an O2 here, but over on this side there's just a single O. Like, where'd the other O go? It's not another product. We don't just have oxygen hanging around. We have to be able to accurately represent the numbers and types of atoms that went in and come out. Key idea here is to realize that when we write an equation like this, we're really grossly oversimplifying it. There isn't just a single H2 in our container, and there isn't just a single O2 in our container. There's containers. There's lots and lots of atoms, many millions of them, of atoms and molecules that are coming together. We're just trying to figure out what the ratio is, kind of the correct mixture between the two of them. So when we actually want to write this particular one in an organized fashion that actually represents or reflects the law of conservation of matter, it's not just one oxygen molecule, it's actually two hydrogen molecules that go in there and one oxygen molecule. And when we're done, we don't just make one water molecule, we actually end up making two. And you can kind of take a look and count this all out. If we only had 2 atoms of hydrogen in and 2 atoms of oxygen in, the math just didn't quite add up. So the way that we would write this is by adding coefficients. Coefficients are these little numbers that we put in our equations, like right here. There's one in front of the H2O. There's one over here as well. Coefficients like that tell us the number of molecules that are going in. So this would be 2 molecules of hydrogen gas, 1 molecule of oxygen gas produces 2 molecules of water. And that gives us an accurate balance, an accurate accounting of the total number and types of atoms that go in and out. Keep in mind when you're doing your accounting and counting all these things up that a coefficient out in front, like on this 2H2O, that applies to everything. That means I have 4 total hydrogens and 2 total oxygens because it kind of distributes across. So when we're balancing equations, a couple big rules, we've got to put these out in front, and then we're going to go through and do some practice examples for this. Number one, you have to make sure that your chemical formulas are written correctly. This is annoying, I know, but that's just too bad. You better remember your chapter 4 stuff. But when you're writing your formulas correctly, it's never okay to go back and change a chemical formula in order to balance an equation. You can't just say, oh, that'd be so much better if there was a 3 there instead. You're not allowed to do that. Once the formula is written, then you're on to the balancing equations part, and that's a separate step. Number 2, when you're doing your accounting, your checking, make sure that you realize or recognize that the coefficients multiply across everything. So you can get some really big numbers of atoms, and that's okay, but you have to keep multiplying that across everything, or sometimes you don't recognize how many atoms you've got there. I'll show you what this tic-tac-toe thing is, this little waffle that we use to keep track of your accounting. It's a little grid that makes it a little bit easier to keep track of, how many of each things you've got. And then at first, it is kind of a guess and test sort of thing. There's some strategies I'll teach you, but for sure, at first you feel like you're just kind of doing it randomly. Like, am I doing this right? Be patient with yourself. As you start to do it a little bit, the practice gets easier and you start to recognize what they are. So we're going to use this little example reaction over here as the one that we're going to talk about today, which is a reaction between magnesium metal and hydrochloric acid. So you can see over in here there's a big strip of magnesium metal in there, and then this whole beaker is full of hydrochloric acid, and it's fizzing. So we've got hydrogen gases coming off, and then we're creating this clear solution of MgCl2. So we want to actually sit there and figure out, well, okay, what's really going in and what's coming out. So here's the little waffle I'm talking about. Just a little mini table. It's not required, but it certainly is helpful, especially as we get to more complex equations, to be able to kind of figure out which elements we have and how many of each. So I kind of draw a little, like almost like a tic-tac-toe to start. And in the center, I'll put the list of the elements. It doesn't really matter what you put them in. I usually just do it kind of left to right as they appear in the reactants. And then there's a spot over here on the left side for the numbers of atoms of reactants, a spot over here for the numbers of atoms of products. So listing the elements off, and then we're going to start to count them up. So how many of each thing do we have? If I look over here, I've got 1 magnesium atom, I've got 1 hydrogen atom, 1 chlorine atom. Pretty easy to count that. Over on the right side here, I have 1 magnesium, 2 chlorines, that 2 only applies to the chlorine, and then we've got 2 hydrogens. So I'll just enter those in there. And now I can sit there and start to figure out, well, is this balanced or not? And I can look right now, and if I tell you I've got the same elements on each side, that's good. But the problem is right here, that I have a different number of hydrogen and a different number of chlorine. So the number of atoms is not conserved yet, and I have to take care of that. I've got more hydrogen and chlorine magically appearing on the right than went in on the left. So now I have to figure out how to use some coefficients that maybe could make this balanced. If I throw a 2 out in front of here, because I need more hydrogen and I need more chlorine, now I just have to go back and recheck my accounting, my little accounting waffle down here, and see if it makes sense. So if I put a 2 here, that gives me enough hydrogens because it's 2 times H, right? And it also gives me 2 times Cl. So I recheck my accounting, mark it in there like that. You can see the 2 numbers that I changed. And now I checked, do I have the same number and type of elements that are present? Same type of elements are there, and now I have 2 of everything that I need to have 2 of, 1 of the magnesiums. This is now considered to be a balanced equation. So this one was pretty easy. All I had to do was put a coefficient of 2 out in front of the HCl in order to balance this out. So what this means is we could read it by saying 1 atom of magnesium reacts with 2 molecules of hydrochloric acid to produce 1 molecule of magnesium chloride plus 1 molecule of hydrogen gas. Could also say this in terms of moles. 1 mole of magnesium atoms reacts with 2 moles of hydrogen chloride molecules to produce 1 mole of magnesium chloride molecules and 1 mole of hydrogen gas molecules. So that's how we would kind of read that out. But it's just a matter of looking at that little waffle, counting them up, and then starting to kind of fiddle with it until it gets to work. So the next few slides are going to have some examples that are a little bit harder and some strategies that you can use to kind of start to attack some of these things. So here's 2 of my favorite strategies that I always start with, and if these don't work, then I go into 3 and 4. Number 1, always start with the most complex molecule and try to make everything else match. You'll see what that looks like here in a second. Strategy number 2, if you've got elements that are present in more than one compound, like in this case oxygen and hydrogen are like all over the place, don't start with balancing those. Start with balancing something else. So here's my equation I'm going to use. This is aluminum hydroxide. This is carbonic acid or hydrogen carbonate. This is aluminum carbonate, and this is water over here. So let's start by just creating our little accounting waffle here, our little tic-tac-toe. And again, I just listed off the elements kind of from left to right as I saw them in the reaction. It doesn't matter what order you do it in, whatever makes you happy. And then I start doing my counting. What do I have? Okay, I've got 1 aluminum. I've got 3 oxygens here, plus there's another 3 oxygens here. That gives me 6 total oxygens. Hydrogens, I have 3 hydrogens because that multiplies. And then I have 2 more hydrogens here, so that gives me 5 hydrogens. Last but not least, I have 1 single carbon. There it is right there. So yes, when you have elements that appear in more than one place, sum them up. Get the total number of hydrogens, total number of oxygens. On the right side, when I count those up, I get some big numbers over here. 2 aluminums. This 3 multiplies across what's in the parentheses. So it's 3 times 1 carbon, and you can see that down in the bottom down here. I've got 3 times 3 oxygens, which is 9, plus one more sneaky one over here, which is 10. And then I have to deal with the number of hydrogens I have, which is simply the ones in H2O. So when I look at this, I've got conservation in terms of the elements that's present. I don't have any magic elements appearing or disappearing, but I'm definitely not balanced in terms of the numbers of atoms of each. Nothing works in this one at all. It's just like scary, shoot me in the face. So strategy number one, start with the most complex molecule. And I sit there and look at all of them. Which one has the most atoms into it, the craziest looking thing that's out there? If I look at these 4 things that are on here, this one right here, this aluminum carbonate, is the one that looks super scary. It's got all 3 elements in it. It's got lots of different subscripts and stuff in there. That's probably the worst one. So I'm going to start by balancing that out. Start with balancing the aluminum and the carbons. I'm going to save the oxygen and the hydrogen for later because those do appear in more than one spot. So that's strategy number 2. So first strategy, let's get those aluminums to work. Because there's 2 aluminums here, I'm going to start by putting a 2 out in front here. And that'll change the numbers of things. I got to do some reaccounting. But that's going to get my aluminums to balance out. So this is what it looks like when I reaccount all the aluminums, the oxygens, and the hydrogens that are changed. Note that the carbon didn't change in this case, but it multiplies all out and it gets a lot of numbers there. Okay, so I got the aluminum taken care of. Part number 2, I can go take these carbons and get rid of those guys because the carbons, remember, didn't match as well. So I could take care of that next. So when I take care of the carbons to get those guys to work, there's my 3 out here, and I put the 3 here because that's where the carbon is. So I want 3 carbons to come out of this thing. Now I have to do some more accounting and check it again because now I've got more hydrogens. I got hydrogens like everywhere. Got more oxygens. Those things are multiplying out. So by the time I'm done doing my reaccounting, this is my total numbers that I have on the left. Looks really scary. It looks like I've gone the wrong direction. Like, oh my God, is this thing ever going to finish? The answer is yes, it will. So be calm. It'll come around. So again, my strategy was I was trying to match the aluminums and carbons that were in here. And that's why I put the 2s and the 3s over here. 2s to match the aluminums, and the 3 here because this is where the carbon lived. So now let's go back and check. What do we have left? Aluminums are working. Carbons are working. We took care of those 2. Now strategy number 2, don't start with the oxygen and hydrogen because they're at the end, but let's take care of them now and see if they work themselves out. A lot of times they'll take care of themselves. So I've got 15 oxygens and 10 over here, 12 hydrogens and 2 hydrogens over here. So what do I need to do to get this number of hydrogens and oxygens to match out? Well, the 12 hydrogens is the easy one because hydrogen's only found here. Hydrogen's, in a couple spots on the left, but I've got to get 12 hydrogens out of this thing. So the coefficient I put in front, because there's a 2 here, has got to be a 6. And if I put the 6 out there, that's now 6 times 2 hydrogens gives me 12. And then if I sit there and do my accounting on the oxygens, it sort of magically just happens to work out, and the oxygens take care of themselves. A lot of times, oxygen will take care of itself. There's not always true, but that's one of my strategies that I use. Okay, ready for the next one? No, right? This is a good time to hit pause, go to the bathroom, get a snack, come on back in a minute, right? Okay, here we go. So next one here. Strategy number 3. Watch for some issues where you sometimes get evens and odds. What I mean by this is that there's an even number on one side and an odd number on the other side. And how do you get those to a multiple that makes sense for both of them? So here's the example one that I'm going to show you right now. This is the combustion of something called ethylene gas. And it's kind of some nasty stuff. It's a component of natural gas, so you've seen it before. But this is a combustion reaction where we burn it in oxygen gas and we get CO2 and H2O. So as I start to do my balancing on this one, we end up, well, there's our little waffle. I'm going to employ strategy number 1, which says let's start with the most complex molecule that's out there. Of all of these, the most complex has got to be this one, the C2H6, because it's got 8 things in there, even though it's not that complicated. And then I'm going to deal with things that maybe appear in more than one spot, like oxygen. Again, it's in 2 places, so that's kind of a pain in the butt. So, going to do my counting up to figure out what I got on the left and what I got on the right, and that one should be pretty straightforward to see what we've got. And now I have to start attacking it. So I'm going to fix the carbons and hydrogens because that's my most common molecule, so I'm going to start there. Because I've got 2 carbons on the left, I put the 2 here to get 2 carbons on the right. And because I've got 6 hydrogens on the left, I'm going to put a 3 here, because it's 3 times 2, to get the number of hydrogens correct on the right. Now I do my reaccounting and see what I come out to. And it looks sort of better, but those oxygens are a mess. So here's the problem. The problem is that over here, this oxygen is an even number of oxygens. It's an O2. No matter what I put out there, I'm always going to have an even number of oxygens on the left. But over here on the right, I have an odd number of oxygens. See that 7 right there? There's nothing I can multiply O2 by that would work here. Yes, I know you can do it at 2.5, 3.5, but no, you're not allowed to do that. Have to be whole numbers. So here's the trick. If you come up with something like this, where you've got an odd number on the right and an even number on the left, and oftentimes these combustion problems where this really comes up, there's a trick. Double everything except the oxygen, and then deal with what comes out. You can believe me or not, but it works faster this way. And again, you can kind of futz with it if you want to, try guess and test, but eventually you'll come up with this. So here's what I'm going to do. Double everything except the oxygen, and then I'll deal with the oxygen next. So here's my doubled everything. I put a 2 out in front of here. Seems counterintuitive, I know. And then I doubled this from 2 to 4, and I doubled this from 3 to 6. And what this accomplishes for me is it makes sure that now I have an even number of oxygens on the right, so that I will be able to get an even number of oxygens on the left. If you take a look, by doubling everything, I kept my carbons and hydrogens happy, and then I have now this number of oxygens. Oh, my battery's going to die. That'll be fun. And let me close that. You go away. Okay. So that now I have the simple matter of trying to figure out what coefficient to put out in front of the oxygens. I need 14. I have to multiply 2 times something to get 14. So that's where I put my coefficient of 7 out there. And then I do my final accounting, and now everything's happy. So again, kind of a trick with the even-odd issues, that doubling everything up sometimes will work out for you. It's just, like I said, another strategy, especially with combustion reactions. Okay, last one, number 4. This is a sometimes strategy. You can balance polyatomics as a unit if and only if the polyatomics stay intact. They don't break apart during the reaction. So here's what I'm referring to. This is a frightening looking thing, and if you try to actually balance this equation out with every single element that's in here, the waffle's like this big, and you're counting up all kinds of crazy stuff. But if I notice this, I've got 2 polyatomics. I've got phosphate over here, and then I have phosphate over here on the right. It doesn't break apart. The other one that I've got is acetate, here it is, and acetate over on the right, and it doesn't break apart either. So this works for this one, where I can just balance them now as a group. So my waffle here looks a little bit different. Because they don't break apart, I can put polyatomics in my waffle and treat them as a group. And now it's actually much easier to balance. So if I pick one thing to balance out and try to figure out what it is, I'm going to start off with, well, I got to start with my counting first. Try to figure out what the most complex thing is. It's one of these either calcium or magnesium kind of ones with all these elements in there. So you can pick one. If you pick a different spot to balance it out, that's fine. I chose to balance out the calciums first, simply because it was the thing that was on the left, so start there, right? It works. So to balance my calciums on the left, I put a 3 over here on the right, and then I do my reaccounting. And now you can see I'm just counting the acetates as a group. It's kind of nice. The second thing that I'm going to do now is, because I've got that kind of craziness going on, I decided to attack my acetates, or my magnesiums, it doesn't really matter. Put the 3 in front of the magnesium acetate over here on the left side, like that. So there it is. And now I do my reaccounting. So now you can see how those balance out. And wait, it's already balanced. It's kind of nice. It's much simpler sometimes to deal with them as units rather than individual atoms. But again, that's if and only if the polyatomics aren't broken apart. So here you go. Here's your hints. Never ever change formulas to balance equations. You're not allowed to do that. Once you've written a formula and the formula is correct, you have to leave it alone. Coefficients have to be whole numbers, and they multiply the whole molecule. So when you're doing accounting, don't forget with parentheses, you got to count everything up. Number 3, check and recheck. Continually check that stupid waffle to make sure you didn't count something wrong. A lot of times when students say an equation or a reaction just won't balance, it's probably they missed counting something somewhere, something that simple. And then there's some hints down there in terms of some strategies that you can use, like identifying the most complex molecule, leaving oxygen for later. That's one of the multi-molecule elements I'm talking about. Watching out for those even odd things and doubling up. Balancing polyatomics as a unit, if and only if they are the one thing. E and F are kind of other sort of hints. Leave oxygen for later. It kind of goes along with B, but oxygen's one of those ones that's a lot of times in a bunch of different spots. And then if you've got single and diatomic elements, they're easy. Leave them to last. Don't balance those first. So there you go. I hope you have some insight now into balancing equations. This just takes a lot of practice. So see you in class tomorrow, and we'll do some more. Have a good one.